Hello everyone, good to see you again. I hope all you are doing very well. In this video, I'm going to review linear regressions. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I first briefly review linear regression models and OLS estimator. This review includes multiple linear regression model, R-squared and adjusted R-squared, how to interpret the estimate, and how to determine the significance of the estimate, and how to deal with a categorical variable as a predictor. All right, let's start with the simplest form of a regression model. Suppose that we have two variables, x and y, and we want to examine how y would change when x changes. This is the regression equation to do so. We say regress y on x, and y, which is what to explain, is called dependent variable, for short dv, and x is called independent variable, explanatory variable, regressor, or predictor. For example, consider a log-log demand model for price elasticity. The log sales is the dependent variable, and the log price is the independent variable. And what we are doing here is to regress log sales on log price. In this regression model, we have several assumptions. First, we assume that a linear relationship between the independent and dependent variables, that is, the change of log sales is proportional to the change of log price. Alpha captures the baseline of the log sales, and beta denotes the rate of the proportional change in response to the log price change. Second, there could be some other factors which are unobserved in the regression. Those unobserved factors are assumed to follow a normal distribution, and this term is called an error. Sigma squared, which is called variance, captures the size of this error. Then, our goal is to infer the values of alpha and beta from data. Let A and B denote our best guess on alpha and beta using the data. OLS, which stands for ordinary least squares, is a method to have the best guess. This method determines the values of A and B by minimizing the sum of squared errors. Let me graphically illustrate how OLS seeks the values of A and B. This is a plot of data on log sales and log price. Suppose that we had certain values of A and B. Those values make a linear line like this. OLS computes the error of each observation, which is the deviation of the log sales from the linear line. Then, OLS computes the sum of the errors squared and determines the values of A and B by minimizing the sum of the squared errors. This minimization problem can be analytically solved. The solution is that P is given by the covariance of the independent and dependent variables over the variance of the independent variable. And A is given by the sample average of the dependent variable minus B times the sample average of the independent variable. Once we find the linear relationship through OLS, we need to evaluate the relationship. That is, we are going to answer these questions. Does knowing the independent variable benefit predicting dependent variable? And how to measure? To answer the questions, we compare the prediction performance with the independent variable to what if we don't know the independent variable? If we don't know the independent variable, which is the log price in this example, the dependent variable, the log sales, is just explained by its mean, denoted alpha, and error. Let null model denote this specification. And this is the regression model with the independent variable, the log price. Then we can measure the size of errors for each model. If the independent variable, the log price, is really informative to predict the dependent variable, the log sales, the regression model's errors are much smaller than the null model's errors. So, by the comparison of the size of errors, we can measure how knowing the independent variable benefits the prediction. R squared measures the predicting performance. It is given by 1 minus the ratio of the sum of squared errors of regression model to the sum of squared errors of null model. If the independent variable is informative, the sum of squared errors of regression model is much smaller than that of the null model, leading to a small value of the fraction and a large value of the R squared. So, the better prediction, the higher R squared value. And R squared indicates the explanatory power of regression model for the dependent variable. So far, I have reviewed regression models with only one independent variable. However, there would be more factors that affect the dependent variable at the same time. For example, sales are affected by advertising as well as price, and various control variables should be considered as well, and some effects could be lasting and carried over. For example, consider a log-log demand model for price and ad spending. Now, we have two independent variables. One is log price and the other one is log ad plus 1. Here, the plus 1 is a widely used numerical device to define log ad effect on zero ad spending. Because the log function is not defined on 0, so without the plus 1, log ad effect is not defined when the fund spent no money for ads at all. This multiple regression model has the same assumptions. The relationships of the independent and dependent variables are linear, and the error is normally distributed. What we are doing here is to regress the log sales on the log price and the log ad plus 1. That is, we are projecting the log sales onto the space made by the log price and the log ad plus 1. OLS determines A, B, and C, which are our best guess of alpha, beta, and gamma values in the same manner by minimizing the sum of squared errors. This is the summary of the components of the regression. Here, we have three variables, two independent variables, the log price and the log ad plus 1, and the constant, or sometimes called the intercept. Alpha, beta, and gamma are coefficients associated with the variable. They are sometimes called parameters of the regression models. OLS estimates the values of alpha, beta and gamma. The estimates are denoted A, B, and C, which are computed from data. Then, interpretation of the estimate of each coefficient is as follows. For the constant, the estimate is the baseline value of the dependent variable if all independent variables are 0. For each dependent variable, the estimate is the response of the dependent variable to a unit increase of the independent variable. Here, we have a logarithmic model, so this response is identical to the elasticity. That is, the percent change of the dependent variable in response to a 1% increase in the independent variable. Alright, now let me revisit the R-squared. R-squared is a simple but powerful measure of the goodness of fit or prediction performance. The better prediction, the higher R-squared value. But R-squared has a caveat. The more variables, the higher R-squared value. That is, just adding a new independent variable always increases the R-squared value. To resolve such caveat of R-squared, we usually use adjusted R-squared instead of R-squared. It is computed from the ratio of the sum of squared errors, but each sum is adjusted its df, which is degree of freedom. The degree of freedom is simply explained as the amount of information used to compute the sum of squared errors. The total amount of information in data is the number of observations in the data, usually denoted m. In the null model, we don't have any independent variables, and we just have a constant which captures the average of dependent variables. Generally, computing the average uses information as much as one observation. So, in the null model, computing the sum of squared errors uses the remaining information as much as n minus 1 observations. In the regression model, we have more independent variables, and each variable has its own coefficient. Generally, each coefficient spans information as much as one observation separately. So, in the regression model, computing the sum of squared errors uses the information as much as n minus p minus 1 observations, where p is the number of independent variables. So, when we add a new independent variable, R-squared increases. But the increase of the R-squared is penalized in adjusted R-squared because the degree of freedom also changes. In the previous exercises, I presented the summary table several times. In our software, we can conduct an OLS estimation using LM function. Running an OLS estimation in R, we have many numbers. Then, which numbers should we look at? The R-squared value is displayed here, and the adjusted R-squared value is displayed here. And this is the table of the coefficient estimate. Now, I'm going to explain how to read the table. This table is the same as the R table in the previous slide. We have 4 columns of numbers with the column of variable names. The first column of numbers shows the values of estimates. The second column shows the standard errors of estimates. This provides information of confidence interval. Roughly, estimate plus minus 2 times standard error gives the 95% confidence interval of the estimate. For example, minus 16.0526 plus minus 2 times 0.3888 is the 95% confidence interval of the intercept estimate. The third column shows t-statistics. It is given by dividing the estimate by the standard error. This value follows a mean zero student t-distribution under the null hypothesis. Usually, we interpret the t-statistics through p-values, which are given in the fourth column. Under the null hypothesis, that is, if the true value is assumed to be zero, p-value implies how extreme the estimate computed from the data is. For example, if the true intercept is assumed to be zero, the estimate computed from the data is super extreme. That is, probability of having more extreme estimate is almost zero. This definition of the p-value can be viewed as follows. Under the null hypothesis, the p-value is the probability of observing the data that generate the estimate value. Here, the p-value is almost zero. So, if we assume that the true value is zero, the probability of observing the data is almost zero. But we already observed the data, so we can conclude that assuming zero of the true value is wrong for the data. That is, we reject the null hypothesis. In general, we use a 95% confidence level. Then the p-value is compared to 0.05. If the p-value is smaller than this critical value, we conclude that the estimate is significant and significantly different from zero. Sometimes, we consider a categorical variable as a predictor. For example, consider store effects. Different stores may have different baseline sales. Suppose that we have a store variable, which indicates the store number like store 1, store 2, and store 3. The size of the number does not have any meaning here. It's just an identifier of each store. In this case, we can use as that function in R to include such categorical variable into the model. And this is an example estimation result with such a categorical variable in R. You may find that only in store 2 and store 3, only these two levels appear in the table. Then where is store 1? This intercept indicates the baseline sales of store 1. And store 2 variable does not indicate the baseline sales of store 2. It means the difference in baseline sales between stores 1 and 2. Thus, the baseline sales of store 2 is given by the sum of the intercept estimate and the store 2 variable estimate. In the same manner, store 3 variable indicates the difference in baseline sales between stores 1 and 3, and the baseline sales of store 3 is given by the sum of the intercept estimate and the store 3 variable estimate. Alright, that's all I have in this lecture. After watching this video, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.